You know, when we think about logic, we usually picture this single, unshakable set of rules for what's true and what's not. But what if I told you that's not the whole picture? Turns out, the very way we prove things is split by a deep, fascinating philosophical divide. So, let's get into it.
Just think about that for a second. What if logic isn't just one tool, but a whole toolbox? And inside, you've got different sets of tools, each designed to build truth in a completely different way. Today, we're going to open up 2 of those toolboxes and see exactly how they tick.
All right, first up is the one we're all kind of familiar with, even if we don't know it by name. This is classical logic, and you can think of it like the master blueprint for the universe, where all the truths already exist, just waiting for us to discover them.
At the very heart of this blueprint is this really powerful and honestly pretty intuitive idea called bivalence. It's simple. Every single statement you can make is either true or it's false. Period. There's no gray area, no maybe. This fits perfectly with a philosophical view called realism, the idea that mathematical truths are just out there, objective facts about the universe, kind of like gravity.
So what's actually in this classical toolbox? Well, it all starts with the axiomatic method, where you build up these huge complex truths from a tiny set of basic, self-evident ones. But the real star of the show is the principle of the excluded middle. This is the big one. It says any statement, let's call it P, is either true or not P is true. This one rule opens the door for some incredibly clever tricks, like proof by contradiction, where you can prove something is true just by showing that assuming it's false leads to a total absurdity. This whole setup is the engine behind what we call first-order logic, which is the absolute workhorse of fields like artificial intelligence.
This one sentence, this is the soul of classical logic. It gives us a world of black and white certainty. Every question has a definite yes or no answer just waiting to be found. It's clean, it's absolute, it feels right. But what if that powerful assumption isn't the only way to see things?
Okay, let's grab our second toolbox now, and you'll see how it builds a totally different kind of structure. This is constructive logic, and it's less about discovering some pre-existing reality and more about, well, rolling up your sleeves and building truth with your own 2 hands.
The main idea here is a complete game changer. For a constructivist, a statement isn't just true because it matches reality. No way. It's only true if you can show your work. You have to provide an explicit construction, a direct proof, an algorithm, something concrete that actually demonstrates it. Truth isn't found, it's built.
So if you go back to that core idea, a proposition is either true or false, and you ask classical logic what it thinks, it gives you an immediate, enthusiastic thumbs up. It's a non-negotiable law of the universe.
But then you turn to the constructive view, and suddenly it's like hitting the brakes. It says, whoa, whoa, not so fast. For a constructivist, you can't just assume a statement is either true or false. You have to earn the right to say that by providing a direct proof. Until you've actually done the work, the jury's still out. Now, the tools in this constructive toolbox are fascinating because they're almost the mirror opposite of the classical ones. The biggest move, of course, is throwing out the principle of the excluded middle as universal rule. And without that, indirect proofs are out. You have to provide explicit constructions. If you tell me a number with a special property exists, you better be able to show me that exact number. And this leads to this wild, incredible idea of formulas as types, where a proof stops being just a logical argument and actually becomes a computational object, basically an algorithm.
And that brings us right to the heart of the matter, the huge philosophical question that splits these 2 worlds. Is truth something we find, or is it something we make?
It really just boils down to this. Classical logic sees us as explorers, mapping a territory of truth that's already there, totally independent of us. But constructive logic? It sees us as engineers, actually building truth from the ground up with verifiable, concrete steps.
Okay, let's lay this out side by side. On the classical side, the nature of truth is realism. It's objective. On the constructive side, it's anti-realism. Truth requires you to show it. This philosophical split directly leads to one accepting the principle of the excluded middle and the other rejecting it. And that choice dictates what kinds of proofs you're even allowed to use. It goes so deep, they're even built on different mathematical foundations. You can think of it like they're running on different operating systems. Classical logic usually runs on something called ZFC set theory, while constructivism uses alternatives like Martin-Luft type theory, which is basically built for computation from its very core.
All right, I know what you might be thinking. This is a really cool philosophical debate, but so what? Does any of this actually matter outside of a logic class at a university? And the answer is, oh yeah, a resounding yes.
Because this isn't just some abstract argument. This whole divide has massive, very real, very practical consequences in one of the most important fields in the world today, computer science.
So remember that formulas as types idea I mentioned? This is where it pays off, big time. In constructive logic, a proof isn't just an argument that something is true. The proof is the algorithm. It's a program. It doesn't just tell you that a solution exists somewhere out there. It literally hands you the step-by-step instructions on how to compute it. The power of this is just immense. This direct connection between a proof and a program is the magic behind tools called proof assistants, like one called Coq. These are used for something called formal verification, which is basically a way to mathematically guarantee that a piece of software is 100% correct. Think about the code running a flight control system, or a medical device, or a power grid. You can't just hope there are no bugs, you need to prove it. And to prove it, you have to build your proof.
And that brings us right back to where we started. Is truth a territory out there waiting to be mapped, or is it a structure that we have to engineer ourselves? Classical and constructive logic give us two profoundly different answers, and honestly, both have given us incredibly powerful ways to make sense of the world. The amazing thing is, this debate is still going on, and it continues to shape the very tools we use to think, to compute, and to create our future.